In this lecture, we're going to talk about observability, linear observability. We'll start with a brief overview of how it fits into a broader controls context, and then we'll take a look at how we can actually derive the observability matrix and provide a little bit of context for that. So in many control system problems, the overall goal is to be able to control some system so that the output state here, x, follows some desired input, xd here. And often that's going to happen through some closed loop feedback system here, where you have some control being applied to some error signal that's passing through some dynamics for your system that's leading ultimately to your output x. And then that's going to be measured using some sensors that give you some measurements y. Now, those measurements probably don't correspond directly to all of your states, and so in many cases you'll need some kind of estimator in order to estimate the state, which would give you x hat, which then you could compare that to the desired value of x to close the loop. Now, before designing an estimator, which may be, for example, a Kalman filter or an extended Kalman filter, it's a good idea to check whether or not it's even feasible for your estimator to estimate the state given the measurements that you have available. So that's where observability fits in. It's a pretty easy way to verify that it's possible to estimate the full state that you're interested in. And further down the line, in subsequent lectures, we'll look at how you can quantify which states are more observable and the extent to which they are observable. So to start, let's write down a little bit of a more formal definition of what it means for something to be observable. Now, for practicality, observability looks at not the current or final state, rather it looks at the initial condition. Mathematically, that turns out to be a lot simpler to evaluate. There are ways to look at the final state. We'll talk about those in subsequent lectures. But so observability lets you determine whether or not there is a one-to-one function that relates the estimate of your initial condition. So is there a one-to-one function that relates that to the collection of measurements that you have? And I'm going to do everything in discrete time here, from k0 to n, so some window of measurements of time, in addition to the control inputs that you have available, also for k from 0 to n. So an observability analysis would tell us if our system's observable, then there is a one-to-one function that relates that initial condition to that collection of measurements and control inputs. So let's think about a simple linear system where we have, in discrete time, k plus 1 is equal to a x k plus b u k. And our corresponding measurements will be y k are equal to c x k plus d u k. Now, if we're really lucky and we have just one measurement, we might be able to estimate our state. So with one measurement, let's see how that would work. If we could take our measurements that we have available, y, k, and we could subtract du, k, because we are assuming that we do know our control inputs, and we do have some model for our system. So if we take that, and then that is equal to c xk, but we're interested in xk, so all we have to do is left multiply both sides by the inverse of c, if it exists. And then we would get that xk is going to be equal to c. And I'm going to write here a plus for the pseudo-inverse because chances are likely that you won't be able to take an explicit inverse. So we'll have the pseudo-inverse here times yk minus duk. Now, if c is full rank and you can take a proper inverse, then that would mean that you could estimate the full state xk given that one measurement. Now, often that's not going to be the case because you may have many more states than you have measurements available. So you have to somehow incorporate additional information in order to be able to do a similar kind of calculation. So to look at how that works, we're going to derive a similar equation, but one for where you have many more measurements. Okay, so let's build that up. So we'll start out with, so this is for many measurements. Let's start with just the 1. So y0 is equal to c x0 plus d u0. That one's easy. Now y at time step 1 further in time will be c x1 plus d u1. Now we want to rewrite this equation so that it is in terms of the initial condition. So we can do that by plugging in our dynamics. So c is going to now be multiplied by a x0 plus b u0. And then we still have the d u1. Now let's see what happens an additional step into the future. So y2 is now going to be cx 2 plus du2. So now we need to plug in x2. So following the pattern from before, we'll now have a squared x0, because we're taking 2 steps into the future, plus a b u0 plus b u1. And all that is still plus d, in this case, u2. Now we can generalize this and make it a function that we could apply to however many time steps we needed. So we can write out y of k is going to be c times a to the k times x0 plus, and now this part gets a little bit confusing, but then we'll simplify it down. So we'll have a to the k minus 1 times b times u0, and then we'll have a whole bunch of these terms. I'll write out the one for k minus 2 here. So we have a, b, u, k minus 2 plus b, u, k minus 1. And we're still going to have the plus d, u, k all the way out there. Now we can rewrite this term here to be a little bit more informative. So let's do that. So we can simplify this whole thing as c a to the k x0 plus c times, and we'll rewrite this sum of matrix products as a product of 2 kind of block matrices. So we'll have a to the k minus 1 times b. We have many things here, a, b, and b. And all of that is going to be multiplied by these control inputs, u0 all the way on to uk minus 2 and uk minus 1. And we still have our plus d uk here. Now you may recognize this guy here. That's the controllability matrix. So we can rewrite this to be a little bit more compact as ca to the k x0 plus c times cursive c k. That's the controllability matrix for k time steps. And then I'm going to call this stack of all these control inputs a cursive u k. And then we still have our plus d u k. Okay. So now we have enough descriptions of measurements at successive time points that we can see what happens if we accumulate a number of measurements over some time window and see how we can use that. So now we can write the following. We can say, let's suppose we have a bunch of measurements. We have measurement from time 0, we have measurement from time 1, measurement from time 2, all the way on to measurement from time n. And now we want to know, can we use all of these measurements together to determine the initial condition? So this guy is going to be equal to, if we take the pattern from above, we can see that, well, y0 was just c, and all of these terms here are going to be multiplied by x0. So we'll look at all the x0 terms. So we had, for y0, we had the c term, and then for y1 we had ca, then for y2 we'll have ca squared, and so forth. So we can copy those over here. So we have ca squared, all the way on to ca to the n. Then we did have a bunch of other terms related to the control inputs. So we have here plus another large matrix, and each of these rows I'll write out as c the controllability matrix at that particular measurement. So in this case, controllability matrix 0, which is going to be 0, and U0, plus D U1. C controllability matrix 1, and the cursive U, plus D U2. C controllability matrix 2, plus D U. Sorry, these should be 0, 1, and 2. 0, 1, and 2. All the way on until we have C controllability matrix N, U, N, plus D, U, N. Okay. Now remember, we're assuming that we have access to the measurements, in addition to the control inputs, in addition to a system model. That means that the only thing in this whole equation that we don't explicitly know is x0. So we should be able to solve for it. To see how you do that, let's simplify this equation a little bit and rewrite it as y, where I'm using that capital Y to indicate that that collects all of the measurements, is equal to, this turns out right here is the observability matrix, the C, CA, CA squared, and so forth. That's what we were after, times x0, plus, and I'm going to call this other big thing here a capital U to indicate that it is constructed from control inputs and things related to the control. So if we're interested in x0, again, as we did before with the single time measurement, we could do a similar thing here where we could say that x0 is going to be equal to the observability matrix inverse or pseudo inverse times y minus u. So now this says that if we had a whole bunch of measurements and we were able to calculate that observability matrix inverse, then the initial condition of our system should be, we should be able to estimate that. So that means that we can go forward in just analyzing the observability matrix O to understand under what conditions it is invertible, how mathematically well posed that inversion problem is. And that's what we'll do in subsequent lectures, where we look at the observability Gramian, interpretation of it, and so forth.